In this video, I will explain how to use the extended Euclidean algorithm. So let's start with a quick definition. The extended Euclidean algorithm is a method for finding the GCD, which is the greatest common divisor, of two integers, let's call them a and b, while also computing integers x and y, such that we can write a times x plus b times y is equal to the GCD of a and b. The coefficients x and y are known as Bézout's coefficients, which have applications in the fields of computer science and encryption. So as an example, let's say we want to find the greatest common divisor between the values 48 and 11. How can we do that using the extended Euclidean algorithm? Well, here's the first step. We're going to identify the larger of the two values, so that would be 48. And here's what we're going to do. We're going to write 48 is equal to, we're going to set it equal to the smaller of the two values, so 11 times q, where q is the number of times that 11 will go into 48. And then we're going to write plus r, where r is the remainder. So let's write 48 is equal to, how many times does 11 go into 48? Well, that would be 4. So we'll say 11 times 4, which is 44, so our remainder would be 4. Then what we're going to do is take this first value that we multiplied by q and move it to the left-hand side of the equation. So we're going to write 11 is equal to, then we're going to take our remainder and move it to this position right here. So we get 4, and then again we're going to ask ourselves, how many times does 4 go into 11? Well, that would be 2. So 4 times 2 is 8, so the remainder would be 3. And what we're going to do is keep repeating this process until we get a remainder of 0. So repeating this process again, we're going to take the 4, we're going to move it to the left-hand side of the equation. So we get 4 is equal to, and then we'll take our remainder and move it into this position. So we get 3 times, 3 goes into 4 one time with a remainder of 1. So we'll just keep repeating this process. Take the 3, move it to the left-hand side. So we get 3 is equal to, take the remainder of 1, move it into this position. So we get 1. How many times does 1 go into 3? That would be 3 with a remainder of 0. So once we get 0 as our remainder, our greatest common divisor between the two original numbers is simply the previous remainder, which is 1. So the greatest common divisor between 48 and 11 is just 1. So let's go ahead and write that right here. So that's the first thing that the extended Euclidean algorithm finds. It finds the greatest common divisor between two numbers. So we found that is equal to 1. Now we want to find Bézout's coefficients. So in other words, we want to write this equation right here. So ax plus by is equal to the greatest common divisor of a and b. So in our example, a and b are 48 and 11. So what we want to write, let's write this. We want this equation. 48 times x plus 11 times y is equal to the GCD of these numbers, which we just found is 1. So we can say is equal to 1. So we want to find what are x and y, Bézout's coefficients. So here's how we do that. We're going to rewrite these equations right here, except for the very last equation where we got a 0 as the remainder, so just ignore that one. So we're going to rewrite these first three equations. And we're going to do so by taking the value on the left-hand side and subtracting the first value on the right-hand side and setting it equal to the remainder. So here's what that looks like. That would be 48 minus 11 times 4 is equal to 4. And this is perfectly valid because this is just 48 minus 44, which is indeed equal to 4. So we're just rewriting these equations right here, where the remainder is going to be by itself on the right-hand side. So for this next equation, that's going to become 11 minus 4 times 2, and we're setting that equal to the remainder of 3. Then we'll do the same for this last equation right here, where we get 4 minus 3 times 1 is equal to 1. And we said we don't need to rewrite this last equation right here where we got a remainder of 0. So recall once again, we want this equation right here. If we look at these three equations that we have, this first equation is almost what we want. We have 48 times, you can imagine there's a 1 right here, minus 11, or if you want to imagine this is a plus 11 times a negative 4, is equal to 4. But notice we want to have a 1 on the right-hand side. Remember, that's the GCD that we found. And right now we have a 4. So what we're going to do is we're going to start with the very last equation right here that we rewrote, and we're going to work our way up to get to this equation. So here's how we do that. We're going to start by writing this equation. So let's say 4 minus 3, And whenever you have something multiplied by 1, you don't even have to write the 1. So really we have 4 minus 3 is equal to 1. Now what we're going to notice is if we look up just one equation, so if we look up right here, we see that 3 is equal to this equation right here. So what we're going to do is we're going to write this equation, or we're going to substitute this equation in for the 3 right here. So when we do that, we get 4 minus, this 3 is going to become 11 minus 4 times 2, and that's all equal to 1. Now, if we distribute this negative right here, we get 4 minus 11 plus 4 times 2 is equal to 1. Now remember, we're working on this equation right here. If we just look up one equation, we see that we're going to need to use a 4 in the next step. So what we want to do is we need to preserve our 4's right here. So notice we have a 4, this is the same as a 4 times 1, and a 4 times 2. So really that's 4 times 3. So what we can write is 4 times 3 minus 11 is equal to 1. And the very last step is we're going to use this last equation where we see that we have a 4, so we're going to take this equation and just plug that in for the 4 right here. So when we do that, we get 48 minus 11 times 4 times 3, and then minus 11 is equal to 1. So remember what we're trying to do here. We're trying to get this equation right here, which involves a 48 and an 11. So we can see a 48 right here. So if we distribute this 3 into the parentheses, we would get 48 times 3 minus, remember, we want this 11 to end up in this final equation, so we don't want to mess with the 11. But what we can do is take the 3 and multiply it by the 4, which is 12. So that's 11 times 12, and then we still have this minus 11 out here at the end is equal to 1. So notice how many 11s do we have? Well, we can imagine this is 11 times 1, and this is 11 times 12, so that's 13. So what we can write is 48 times 3 minus 11 times 13 is equal to 1. And this is almost exactly the equation that we want. We just want a plus sign to be right here. So if we want, we can change this to a plus, and we'll make the 13 a negative 13. So now what we see is that we have written this equation right here in this format. And what we can see is that x is equal to 3 and y is equal to negative 13. So let's write that right here. So these are Bézout's coefficients. So that is how you can use the extended Euclidean algorithm to find both the greatest common divisor between two numbers along with Bézout's coefficients that satisfy this equation right here.